Hello everyone, Atheatos here. And yeah, it's time again to have some fun with my heavily modified Soyo 486 motherboard. And this time we play with some Intel Pentium Overdrives. Now these ones are basically Pentium core CPUs that are designed to fit the 486 socket, socket 2 and socket 3. So this is the very first Pentium Overdrive. A lot more followed this for different sockets. And basically there are so many strange things about this one that yeah, okay, we have a lot to cover today. So as usual, this video will have everything, you know, overclocking, underclocking, and of course a lot of modding. The comparison here would be against my IBM-5X86. Just recently I did a video on this topic, and regarding overclocking I managed to get this to 192 MHz. I also discussed on this video a lot of details regarding this motherboard and the BIOS settings. I will not repeat this information now, so in any case it is highly advised to just check my previous video first. So Pentium Overdrive, what is this all about? And for sure we have to start a discussion about the differences between Pentium and 486. And there are quite a few of these. Most importantly, the Pentium processor was the first one from Intel that had the superscalar architecture in combination with speculative execution and branch prediction. So basically, to put this simply, the Pentium processor had doubled the number of execution units. So this means that in theory, compared to a same frequency 486 CPU, the Pentium can execute at maximum double the amount of work. So at best a Pentium at 100 MHz should be as fast as 200 MHz for 86. Then the second very important improvement was a faster floating point unit, and this actually gave an edge to the Pentium CPU as more and more games back then switched to floating point operations. Then there are a few changes with the organization of the cache memories, but then okay, the last very important difference is that the Pentium CPUs typically use a 64-bit data bus that basically doubles the bus throughput. So in the end the Pentium processor has doubled the processing speed, doubled the data throughput, and a better floating point unit. However, here this Pentium Overdrive, as it is made for the 486 socket, it has a special 32-bit bus interface, something that is totally unique within the whole Pentium series. To compensate for this loss, these Overdrive CPUs have doubled the amount of level 1 cache to 16 kilobytes for data and 16 for instructions, something that is also quite unique within the whole Pentium series CPUs, as no other non-MMX CPU has this much. Now there are only two Pentium Overdrive models for the socket 3, the Pentium Overdrive Processor 5V63 and the Pentium Overdrive Processor 5V83. Both are using a 2.5 multiplier, and the difference is with the bus. The first one has 25 MHz and the second 33. And again we see here the L1 cache 32 kilobytes, 16 and 16. So yeah, these are marked as 5V, and for sure you have to set your 486 motherboard for that. However, the core is at 3.3 volts. So okay, basically here on the ceramic you have this linear voltage regulator that generates the CPU voltage from the 5V. Now both of these were released in 1995, and an interesting thing here is that the first one, the 63 MHz, was released in February, while the 83 model was released in October. And that is a significant gap here. That probably means that Intel had a hard time pushing these frequencies higher. Now if we were also to check the original Pentiums, starting from socket 4, first of all, these were at 800 nanometers, had half the amount of cache and topped at 66 MHz. Yeah, these were released back in 1993. And then in 94, we have the first socket 5 CPUs at 600 nanometers, something that is quite more relevant to the Pentium Overdrives here. These were released up to 100 MHz, but again the cache is smaller. More or less all later models used 350 nanometers, so yeah, all these are a totally different class. However, the funny thing is that okay, the cache is always 8 and 8, and only went to 16 with the Pentium MMX in 1997. Now I have here one 63 MHz model and one 83. Well, actually I have two more of these, but the other two are on the operating table and you will see them later. And yeah, here is the voltage regulator, and on the top there is this specially engineered cooler First of all, okay, you have this cutout here for the voltage regulator. Secondly, it communicates with the CPU, and if this is not plugged, the CPU deactivates the 2.5 multiplier and just works in 1x mode. And of course, okay, look at this clip. You have these two little plastic things here. You push them in and you just remove the fan, just like that. And here you have a hinge. Yeah, you can see how precisely engineered is everything, both the heatsink and the fan, and they just perfectly fit each other. So you put this here, then you just push it back. And here you have the contacts on the CPU. On the fan side, these contacts are spring-loaded, and yeah, all this is totally crazy for 1995. By the way, there are two ways to tell these two models apart. The one is just below the fan. So if we remove here the fan, the model is clearly stated here. So this is the 63 one, and yeah, let's see. This is the 83 one. But okay, most importantly, on the top right corner, yeah, here on the ceramic, the one is marked clearly as 63 and the other as 83. So that is all the general information about these CPUs. And now we are going to go to the modding part. My goal, of course, is to improve the cooling options here and mod the voltage regulator so that we increase the V-core. So first of all, I started by removing the stock cooler. So to do this, okay, first of all I remove the fan, and then I use the knife here. You just have to push it a little bit in, yeah, something like that. So yeah, this is the first step, and then I just had to hit it with a plastic hammer, somewhat gently, and yeah, slowly but surely this goes in deeper, and then here I continue, and we are here. So in the end, just a little bit more, and yeah. It's actually very easy to remove the metal here. However, yeah, this is where the real pain begins. You see, this glue here is something like ceramic cement, so it's really like a stone, and it doesn't glue that strongly to the metal, but to the ceramic CPU it is a totally different story. So now, if we want to use any serious cooling here, we have to make this surface flat and remove this gray stone thing here. I tried to scratch it with a knife or something, but it doesn't really help. So in the end, at this point, the fastest way, and okay, a little bit brutal, is by using a Dremel with a diamond tip. Of course, I first had to soak it a bit to isopropyl alcohol, just to reduce the dust here, and then put a little bit more any now and then. Again, all for the dust. I mean, the alcohol does not dissolve anything here. And the Dremel works actually quite fast. Then I wash it periodically with more and more alcohol to remove the dust. And then of course continue here. And wash. So after a few times I got something like this, with most of it removed. And yeah, now it's time for some sandpaper. And again I had to do this many times. But okay, slowly but surely in the end I arrived at this point. And yeah, there is in the end some discoloration here, and for sure the ceramic CPU got scratched a bit by the Dremel, but in the end nothing too significant, and it is quite smooth on the touch. So yeah, of course in the end I had to wash everything under the sink to remove all this dust, and this is the final result, all clean and nice. So now that we have removed the stock cooler, of course we have the problem with the CPU multiplier, and this now is the first mod. So let's focus on these 3 points here. The first one is the 5 volt supply, the second one is ground, and the third one comes from the fan. Now the interesting thing is that I used an oscilloscope here to check the signal, and there is no frequency here, nothing, just DC. So basically this pin here is a digital input that just tells the CPU if the fan is working or not. If you don't have a fan attached, this pin is around 2.5 volt. But then the fan pulls this pin to the ground. Now if you slow down the fan, at some point the fan fails and stops pulling this to the ground, so it returns to 2.5 volts. If it detects a fail, it continues to signal a failed fan until you actually completely cut the power. So yeah, in the end the fan makes all the monitoring and it just informs with a digital signal the CPU. If the signal is high, the CPU works in 1x multiplier. If the signal is low, this is the normal condition and the 2.5x multiplier. So all this means that if we go actually here and sort out these two pins, so force the sense pin to the ground. The CPU will work with a 2.5x multiplier, and certainly you can just directly sort these two, or put here a jumper so that you have the option for the two multipliers. But in my case I just put here a very small 1K resistor. Yeah, not actually needed, but I always like to use 1K resistors just to be in the super safe side. So here is the very small SMD resistor, and of course I apply some solder first. Then I solder the resistor from the one side and then the other. Of course at this point there is a lot of leftover solder here, and I want to clean this up so that I will have a big flat surface for the cooler. So I used some wick here with some flux and basically removed everything. The very little that is left is enough to hold the resistor in place. So yeah, this is the final result. I got in the end something super smooth here. So now at this point the next target is the voltage regulator. The model is LT912. The datasheet of this chip there is nowhere to be found. But either way it's clear that this is a fixed linear voltage regulator. The output voltage actually is not 3.3 but 3.45 volts. And unfortunately this is not the best, as it has a voltage drop of around 1.4 volts. That means that if the output is at 3.5 volts, the input needs to be at least 4.9 volts. Now okay, the datasheet of this specific chip might not be available, but okay, here is from another one that has very similar pinout. So the bottom pin is the adjustor ground pin. Of course this is a fixed voltage regulator, so in this case it is ground. The middle one is the output and the top one is the input. Now it doesn't really matter if this is an adjustable or a fixed one, because this ground pin here is the reference voltage. So as the voltage regulator tries to keep the voltage difference between the output and the ground fixed, we can just play with a ground pin and so adjust the output voltage. So here is an example, and this is applicable to all fixed voltage regulators. So yeah, the goal is to raise the voltage here in the ground reference point, and one way is just by using some Schottky diodes here. Every one of these will raise the ground voltage by 0.2 volts. So by sorting some of these, you can get your original voltage plus 0.2, plus 0.4 and finally plus 0.6. So now we have 3. So let's see now, the first diode actually has 180 millivolts, the second has 360 millivolts, the third has 540 millivolts. So the final output is at 3.85 volts. If I do this again, but I sort, I don't know, one of these. Now this point is 180, this is 360, and the output has fallen to 3.66. Now another way to raise here the voltage on the ground pin and do this mode is with a resistor. Typically voltage regulators have a small current here. This is usually around 5 milliamps, but this is not standard and might vary depending conditions. So in the end, okay, for sure, the mode with the diodes should have a more stable output. However, the diodes are very sensitive to temperature. So yeah, either way, it is possible to raise the voltage of a fixed voltage regulator. But of course, with a real adjustable one, you can get better accuracy. So okay, if we assume here 5 milliamps, then 100 ohm here should give plus 0.5 volts. Let's see. Yeah, this is around 500 millivolts, and the final output is 3.81. Yeah, all as expected. Now, no matter how you do this mode, if you use the diode or the resistor, but okay, especially in the resistor version, it is a good idea to also have a capacitor here, and maybe a quite big one, maybe 100 microfarads, and stabilize this node to the ground. Yeah, so that with some transient stuff here, this node does not bounce around. Also, of course, here you can have a variable resistor, and in this case something like a 200 ohm one is more than enough. So when I first started playing here, I hit the limit very fast. And okay, first of all I did this very fast and dirty mode of just placing a very small Schottky diode here on the ground pin. Now the size of the diode does not really matter as the current is very small, as I said, around 5 milliamps. The actual model that I used is this one. Yeah, it really does not matter what you use. I just use this because it comes in a very small 0603 package. Now this directly gave me a V-core just above 3.6 volts, so a rise of around 0.2 volts as expected. However, yeah, I mean my 63 MHz models, even with this mode, could not do above 80, and my 83 MHz model could not do stably 100. Yeah, I have seen other people doing 100 without modifications on air, but I was again super unlucky here. So then of course I can raise the voltage even higher by placing more diodes. This in the general case will not work because of the 1.4 volt minimum dropout of this voltage regulator. In my case for sure I can eliminate this problem with my little device here that can just provide the motherboard with something like 5.4 volts. Now another way to handle this dropout issue is maybe by replacing this chip here with something more modern, like a low drop voltage regulator. But nearly all of these have a different pinout here and are also very expensive and usually out of stock. In the end we need something that can easily handle even peaks up to 5 amps. Then the ones that have the similar pinout in the end can only give you marginal improvements. One such model is the LT1085. Yeah, this is available in a very similar package and everything is the same. You can maybe also go for the adjustable version. So there with some resistors you can have a more accurate setting. However, in the end there are more problems with this approach here, so it's not ideal either way for high overclocking. You see, the problem is that this voltage regulator dumps heat on the ceramic of the CPU, and that is actually a lot of heat. So here maybe 1/3 to 1/4 of the generated heat is from the voltage regulator. So in the end, if we get everything into account, it is better to remove this and have something external to generate our V-core here. And yeah, this is what I did in the end. Unfortunately, I lost the footage of me removing this chip. It's not the easiest thing to do, but actually it's also possible with just a soldering iron. You just have to hit individually all the pins and lift them up. So finally you are left with a huge pad. And of course this is the hardest one to remove. But okay, with a little bit more heat it is possible. In my case, of course, in the end I used rose metal to lower the melting point of the solder here. So the removal was quite easy in the end. So now after you remove this, you have this large pad that is actually unconnected on the CPU. You have the bottom pad that is ground, the middle one that was the output of the voltage regulator and so the power input of the CPU, and the top one that is the 5 volt that is provided by the motherboard. Okay, and the question now is how I will generate this voltage that I need here. Some people are just using some diodes to drive the CPU voltage directly from the 5 volt rail. I don't think this is a good idea. You see, there are two problems with the diodes. First of all, okay, for sure they're not too stable with big fluctuations in current. But I think the most important problem is the stability with temperature. So basically when you boot up and 10 minutes later you will get a totally different voltage, maybe by 200 millivolts apart. The other thing is the amount of steps you get. If you use normal diodes, its diode is around 0.7 volts. Then Schottky diodes maybe 0.3. So with Schottky it might be possible to get nice steps, but you would have to place a lot of them. And this time this should be fairly large to handle the current. So either way, yeah, I don't like this diode solution. So then, okay, we need an external voltage regulator. And of course my thought was to just use the voltage regulator I have on the motherboard. You see, last time we did a lot of modding here and now I have 8 very nice settings from 3.6 to 4.4. And this voltage regulator, okay, normally is rated to 2 amps, but can certainly do 3. Now the Pentium Overdrive, even at 100 MHz with 4 volts, is around 2.4 amps. So in general it is okay. However, of course, if you push it even higher, then it can cross the 3 amps mark. And then, okay, this is not that useful. However, for now I will take it. So can someone just come here and sort these two? And then go to the motherboard and change the setting from the 5 volt to the onboard voltage regulator? Well, not really. You see, there are two types of voltage inputs to a 46 CPU. Okay, the Pentium Overdrive is very similar. The red ones are all for the voltage of the core. This VCC5 is the 5 volt input that is always there for the I/O. Now 5V CPUs like this Pentium Overdrive actually sorts everything together, so both the red and this VCC5, while the 3.3 CPUs differentiate these two. So yeah, with the Pentium Overdrive, even if you go here and you change the setting from 5V to 3.3, the CPU sorts everything together, so in the end you get again 5V. Not only that, but this is a little bit dangerous because the CPU is only powered by one pin. So yeah, in the end, what I did here. And the answer is simple. I just used an external cable to drive directly the output of the voltage regulator to the CPU. And the nice thing is that, yeah, these two unused pins here are exactly what we need. So just a wire that connects to these two will do the job. So now here to our very clean CPU. The first and the last two capacitors are connected to the output. These are actually only 3 microfarad each. And now that the power comes with a wire, maybe it's a good idea to add a little bit more here. So these two, each one is 100 microfarads and can be nicely placed here on these two bottom pads, as one is ground and the other is the output. So yeah, okay, I soldered this. So this is the result. And then just to make my life easier, I also soldered the wire from the middle pin. And now I have a very nice large target here where I can just connect my voltage input. And yeah, this is what I did here. Maybe in the end I also added an extra large electrolytic capacitor, 1,500 microfarads. And yeah, this nice cable just goes in and plugs here. And that's all. Very nice, right? Now okay, the very high voltage settings here may be a bit unusable because of the high currents, but up to 4.1 volts this goes very stable. In the future I will make a new custom voltage regulator specifically for these CPUs. And okay, the other nice thing I have here is that now we have a lot of clean space, so we can place any cooler we want. But of course the nicest thing is that I can place a Peltier, and a fairly large one, a 40x40. And this time it nearly fits completely here. So yeah, I really like the final result. Now of course on top goes this tower cooler. In the end a Peltier or some passive cooling with just a case fan blowing on top, it doesn't make a significant difference. Okay, sure, I got 4% more overclocking with the Peltier. But yeah, okay. The thing is that even the Peltier cannot really freeze the CPU. It just drops the temperature to around 15 Celsius, maybe 10. That is also good, but nothing spectacular. So yeah, this is all with the mods and the hardware, at least for now. Let's go directly and see a little bit the BIOS and then the overclocking results. And yeah, here there are not a lot of differences. There is one additional setting, the CPU internal cache, that you can set to write back or write through. However, this is actually not working, so you know what is the next thing I did. Okay, I'm sorry, I have one additional mod to show you. So this is the pinout of the Pentium Overdrive. Everything within the red square is the old 486 pins. The other are the additional ones that are used only by the Pentium Overdrive. And down here is a write back, write through pin. Yeah, the 486 has a similar pin, but it is in a different position. So, okay, this pin, if you pull it down, then the internal cache is forced to write through. And you can very easily do this by placing here a 1K resistor between these two pins. Yeah, as simple as that. Now it doesn't make a lot of sense to do that. I checked again, okay, there is a 10-15% reduction in every benchmark. So yeah, not a good idea. But either way, if you want to do some benchmarking, you can do that. Then another interesting pin is this blend. According to the datasheet, this controls if the write-back cycles will attempt to run as burst cycles. To my understanding, this is similar, if not the same as this CPU burst right here in the BIOS. And well, the reason I'm discussing this now is because some of my CPUs came with this little interposer here. Yeah, this was placed on the pins of the CPU. It has a nice fit, but okay, in the end the only thing that it does is to sort these two pins. And yeah, this is basically enabling this BLEN pin by connecting it to the ground. However, okay, I don't know, I tried with this or without this and all these settings here, and I didn't notice any difference in the benchmarks or any other behavior. In the manual it stated that you should enable this if your motherboard supports burst mode, and that it has no effect when the processor is in standard bus mode. So I don't know, this might be relevant for some other motherboards and systems, so it is something that I will retest in the future. But okay, for now it didn't have any effect, so in the end I did all my tests without it. So the time has come, and this is what I finally got. Yeah, I managed to overclock to 110 MHz with a bus of 44.2. I'm quite pleased with this result. I mean, the CPU before the mods could not even do 100 stable, even with some extra voltage. By the way, even when I used just the small heatsink with a fan, I was able to do here 106 MHz. And yeah, both configurations were completely stable. Now in order to go above 110, okay, maybe I need a better CPU. I was again very unlucky with the CPU lottery. Then okay, here is Landmark. Landmark cannot detect the CPU correctly. Now the CPU score is just a little bit lower than my 192 MHz 486, but the floating point test is maybe 80% higher. Yeah, that's crazy. Then system information here, and okay, everything is detected correctly. Pentium at okay, 111 MHz, and this is the CPU score. The 486 actually scored here something like 20% higher. Then here speed is, and again an Intel Pentium at 111 MHz, and the score is around 82. This was 72 with the 486. And the very interesting thing is down here. First of all, the level 2 cache and the memory throughput are significantly lower, as okay, in this case the bus was only at 44 MHz, while before it was at 64. And then you have the L1 cache, and the speed is maybe 20% higher. And yeah, by the way, here it only detects the data cache. Yeah, in reality the total L1 cache is 32 kilobytes. The disk speed, okay, it is the same as before. Now cache check tool, and again Pentium clocked at 110.6 MHz. And okay, again it only detects the 16 kilobytes of data cache. However, okay, this time all these numbers are lower than the 486. So yeah, maybe this is a little bit strange regarding the L1 cache. Then okay, here check it, and the real-time clock test passes successfully. And this is CPU speed. The CPU score is 10-20% lower, but the floating point speed is 10% higher. Yeah, it's clear we have a pattern here. The video speeds are all higher, I don't really know why. And yeah, the hard disk speed again the same. And now with the dedicated VGA speed tools, yeah, here the performance is significantly lower, maybe 20-30%. And this is what I was expecting to see in the first place, all because of the lower bus speed. And here again in vid speed the video bandwidth is around 17,000. It was before around 25,000. Again maybe a decrease of 30%. Then here also the dedicated floating point unit test, CPR for Dodge. And this completed at 74 seconds. That is, I don't know, a significant improvement around 20%. And of course the sound checks here are the Pentium ones that to my understanding are completely IEEE compatible. So now time for the main menu. And first of all 3D bench with option 2. 96.6. Yeah, not bad, but certainly lower than the 486 machine. Then Chris 3D bench with option 3. Again, not bad, 76.1 frames per second. Then PC player benchmark with option 5. $27.2. And then of course time for some Doom, full details. And that is 53.8 frames per second. That is actually significantly lower than the 486 machine. And this is the biggest difference of about 25%. Of course now before we run Quake we will change this from write back to write through. So now here we go. And yeah, okay, this is probably the moment everyone was waiting for. And here we have 26.4 frames per second. Yeah, not bad at all. A significant improvement over the 486 machine. So now here is the table with all the results. And the two first lines are from my previous video and the AM5X86. Yeah, at 192 MHz. That is basically an overclock of 44%. So then here we have the new measurements from the Pentium Overdrive at 110.6 MHz. That corresponds to a 33 MHz overclock. Yeah, this time I had to raise the voltage a little bit higher at around 4.1 volts. And of course I measured everything, both in write through and write back mode for the level 2 cache. And things look here very similar. Every benchmark performed better in write back mode. And the only exception is Quake. So then down here I have the direct comparison between the two setups. For the calculation I used the average between the write through and write back mode. So here with 3D events, the Pentium is around 12% slower. With Chris 3D events and PC Player benchmark, it is something like 5% slower. And then Doom we have a huge difference, where the Pentium machine is something like 25% slower. However, in Quake, the Pentium machine is more than 28% faster. So in total, the integer tests were 16% slower. But yeah, okay, in floating point tests, the Pentium was 7% faster. So yeah, on average, the Pentium machine is something like 5% slower. However, okay, this is a bit misleading. I mean, in the end, it doesn't matter if you're slower on something that either way plays just fine. And here as an example, of course, Doom. You see, in the end, Doom is frame capped, so 53 or 71 does not make any difference. However, okay, here in Quake 2026 is a difference that you will definitely feel. And basically, even if the Pentium machine underperforms in every other benchmark, in the end it's very unlikely that you will notice any difference on older games. So in the end, the Pentium setup is probably preferable. Then down here I also measured the Pentium Overdrive in 1x multiplier mode and the same bus. Well, of course, like that I also tried to push the bus higher, but this is impossible. For sure my motherboard can handle higher bus speeds, but I don't know, there is an issue here with the Pentium Overdrive. I tried, I don't know, 46 and it didn't boot at all. And even with this 44-24 MHz, the 63 MHz model was also not able to boot. So I'm not really sure what is going on here. I can only give you two assumptions. The one is that just the bus interface of the Pentium Overdrive cannot run in these high frequencies. And the other is that, okay, there is probably an internal PLL to the Pentium Overdrive. There is a good chance that the input of this PLL cannot be set too high. And maybe, yeah, the PLL there is optimized for 25 MHz when you have the 63 model and 33 MHz for the 83 one. So yeah, the conclusion here is that the 1x mode cannot help us break any performance records. And also, fortunately, the multiplier cannot be set at any other setting. However, there are some interesting conclusions here from these measurements. Yeah, here the comparison between 1x and 2.5x. And we can see that in all benchmarks, the 1x setup was faster than half the speed of the 2.5x one, though the clock is only 40% of that. That just means that the 2.5x setup, it is actually severely bottlenecked by the bus throughput. Yeah, in the end, having just a 32-bit bus for a Pentium machine is just too limiting, and higher multipliers make this even worse. So I think it was a mistake going here for a 2.5 multiplier. Something like just a 2x multiplier sounds more reasonable. And I bet that if they had released something like 2 times 40, so 80 MHz, would have been actually faster than this 83 MHz model. But okay, all this is of course speculation and now history. So that is all with the overclocking and measurements. Time to go and see some underclocking. And yeah, things here are very similar to what we managed to achieve with the 5x86. Yeah, I got again a 2.5 MHz bus. And of course, okay, the CPU was set in 1x multiplier. So 2.5 is also the final frequency of the CPU. Now with the Pentium Overdrive the system takes too long to post, so too long to just show anything in the screen. And with this underclock, okay, it basically takes 2 minutes from the time you turn on the switch until you see anything. But after that everything is more or less okay. So okay, the BIOS settings are very much the same. One strange thing is that here if you disable the internal cache, this disables both the L1 and the level 2 cache. So with this disabled, this is a bit irrelevant. I don't know why. In theory you should be able to disable and enable these two independently. Could be a bug in the BIOS or the chipset. Then here the boot up system speed, I left it in high and I control the deturbo function with the jumper, just because going into the BIOS takes too much time. By the way, okay, the deturbo function does not actually halve the bus frequency here. According to the datasheet of the chipset, this just idles the bus periodically, and that is probably for the 2/3 of the time. However, I don't know. I mean, I did a lot of measurements and most of the benchmarks and tests performed exactly at the 50% mark. So in the end, I don't think the very fine technical details here matter. And based on performance alone, we can just think of this as just halving the bus speed. And then just keep in mind that this is not that consistent. So as with my 486 machine, the clock generator actually generates a 5 MHz clock with a 2 MHz crystal and a 2.5 multiplier. But then due to this deturbo function, the effective clock is something like 2.5 MHz. Now with the same crystal I can easily go to 3, 3.33, 4, 5 or 6 MHz just by changing some jumpers. So overall very nice. Okay, the rest of the settings are here, just the slowest options. And then here in the PCI configuration setup, something that I forgot last time. And it goes to also disable these 3 options here, thus reducing the video throughput. And here we are. Well, of course I edited out all the booting process. I'm keeping the pain for myself. So let's now have a look. And yeah, you see what the situation is here. So let's see landmark. And yeah, here for sure we have a lower score than with the 5x86. Now a little bit of cast check tool. Yeah, Pentium clocked at 2.4 MHz. And you can see again here some ridiculous numbers. So here is system information. And okay, this is more or less detected correctly as a Pentium at 2 MHz. Let's see if we can run the benchmark. Yeah, this is ridiculous. So now here is check it. And yeah, the main system benchmark. Yeah, this cannot detect the Pentium CPU. It is reported as a 486 at 5.38 MHz. Now the result here is lower than I got with my 5x86 machine. This is something like 20% lower. And yeah, this is only 0.33 times the IBM PC-XT. And then here with the video system benchmark, the situation is quite similar, around 0.3 times. Now let's enable the turbo and check again. And yeah, first of all, the reported frequency is doubled. Okay, this is not 100% doubling here, but quite close. And that is more or less true also for the scores. We are now around 0.7 times the IBM PC-XT. Yeah, even with the turbo function enabled, we are still below the original IBM PC. So now time to check some games. And I have disabled the turbo again, so we are at 2.5 MHz. Let's see round 42. And yeah, this is slow. Very slow. So next is Defender. And yeah, I don't know, this is definitely slower than it should be. But this is the only way I can play this game, it's too hard. And here is flight. And well, this is absolutely ridiculous. This is so slow that yeah, it's actually impossible to play. What can we say? A Pentium machine is not enough for this game. Yeah, absolutely ridiculous. In here though, it looks not that bad. Turbo is nice and good, but it is a bit inconsistent. Not a real problem, I mean either way, even with the turbo enabled, we are slower than the IBM-XT. So yeah, now I tried a bit to get a configuration where it is closer to the original IBM PC-XT. And first of all, I'm running now at full speed, so with the turbo enabled. And then I changed the clock generator from 5 MHz to 6.66, so this is also the frequency of the CPU. As we see here, now this scores 1.02 the IBM PC. Also the video performance is quite good. And let's see some games. Round 42. Yeah, this is quite good, but maybe still a bit slow. Yeah, okay, it is slow, but I like it. For sure I can go higher, I can go to 8 MHz. Yeah, Defender is still okay, but I definitely prefer this lower. Because of these stupid red things. And let's see flight. Okay, this looks quite good here. Yeah, this sounds great. And here also. So okay, you get the idea. Maybe you have to play around a bit with the settings for every game individually, but in the end all these are totally playable on this Pentium machine. So here we are, we did it. A Pentium CPU on a 486 motherboard, clocked from 2.5 MHz to 110.6, and yeah, okay, basically everything between. And a system now that can run everything from the first IBM-XT games to even Quake. And actually way better at this compared to our previous attempt with the AM5X86. So yeah, I can only be happy with these results. However, not really. You see, okay, 110 MHz for the Pentium Overdrive is probably a record, but I still need to check more CPUs. I might do one or two more. In the end, these are not the cheapest ones. And of course, I'm already designing a specialized voltage regulator here, and this should also contribute a little bit. Of course, all this in a future video, so like, comment below if you really want to motivate me to do this. And then of course subscribe if you don't want to miss all that. So yeah, that was for today. I really hope you liked it. That was a big one and not that easy to do. It's very hard to remember all these details and put them in order. And of course in big videos there is always room for mistakes. I hope I did a good job. So that is all, and yeah, see you again next time.